I mean, we're doing good. or not. I'm doing good. Yeah, it's Saturday. I don't have to go anywhere in the morning, at least. So I could have slept a bit more, but you know, some events.
Yeah, my family waiting me on a sea already, so I.
Yeah, Alex is like a bit out of his usual.
Yeah, everything's good.
Premise. Cool.
Nice.
So we started on YouTube. Behavior business.
Yeah.
Yes.
Yeah. Well, I suppose it's 10 a.m. We could be really punctual, like the country I'm living in. So yeah, hello everyone. We are X Technology and welcome to our event number 13. So I know that in some countries it is an unlucky number, but I hope, or I am sure that for us it's a very lucky number. And I mean, the greater this number is, the luckier and happier we are. So it's just perfect. Yeah, today is Saturday, our usual time, morning. So we are happy to see everyone who joined at this usual time to listen to something really interesting. And today we have a really great talk, which Mila will present to us in a couple of minutes. It's called Knowledge Graphs, or yeah, I don't know if it's an introduction to knowledge graphs or it's something advanced. Honestly, I'm not really into this topic
something
yet.
In the middle, but let's say it's.
Yeah. But I'm really keen to know about this topic. And I would really hope that we have no troubles with connection and we will be able to see the presentation and to hear every cool detail from Mila.
Yeah.
But at this moment, I suppose we have some small technical issues, which will be resolved for sure. And in the meanwhile, we should tell some stories from our life. I don't know.
Yeah, like we said, I have some knowledge. I know what the graph is. I mean, what. Oh, Mila is back.
I don't know. That happened.
Yeah, no worries. We're just telling some funny stories about the graphs and so on. Entertaining. Yeah, and we are almost ready to give the mic to you, but I suppose it would be nice if you share your screen and we can go.
Probably.
Also, for those who are watching us on YouTube,
yes,
please drop your questions into the chat, so we're going to show them eventually on the event.
Yeah. Well, I suppose there is nothing more to introduce. Mila will now have a great talk about knowledge graphs. Yeah, and please go.
Thank you. I will take over the introduction. So hello everyone and welcome. Today we'll talk about knowledge graphs. My name is Mila Glavaški, and let's say a few words about me. I'm a PhD candidate doing research in intersection of data science, machine learning, and biomedicine. Also working as independent consultant in the meanwhile in fields that everything that I did before, so going all the way from laboratory medicine, management, to bioinformatics, data science, and machine learning. Small warning at the beginning. Although it's connected, we won't talk today about RDF, the standard data model for data interchange on the web. Also, we won't talk about OWL, Web Ontology language, which is widely adopted language supported by World Wide Web Consortium, which is responsible for web standards and take care of internet too. Their mission is to lead the web to its fullest potential. Also, we won't talk about semantic web neither. It's the vision about the extension of existing World Wide Web with vision to make search engines not only index data, but to understand it. These are huge topics themselves, so we will skip it for now to make some space for knowledge graph. So back to knowledge graphs. They are also called semantic networks. They are knowledge representations where we represent entities as nodes and relations between those entities as edges. So we will repeat this all the time. Entities are nodes and the relations between them are edges. And with this knowledge, we think of whatever is known. We can think of everything that is shown on that knowledge graph explicitly, but we can also think of that knowledge as wisdom that could be extracted or inferenced from that explicitly. We'll talk more about this later. We have plenty of definitions on knowledge graphs, so let's go through some of them. So it's not completely stable term. The essence is always the same. So we can also say that knowledge graphs are directed labeled graphs in which labels have well-defined meanings. So we know what nodes are, we know what edges are, and that makes something knowledge graph. The main idea is to get the data in order to extract something else out of it, or to understand that represented data better. So in visual way, we can perceive the same data better. We use knowledge graphs in applications like integrating data, managing the data, or inferencing some conclusions out of it, usually at the large scale. Let's try with more definitions. Knowledge graph represents a collection of interlinks, descriptions of entities that could be anything. So entities could be objects, people, event, concept, whatever. And then we put that data in context while linking with all that these edges. And then we have a platform for something bigger. As we said, entities could be whatever, relationships between them also. And then at the end, when we connect all those nodes and edges, we have something like a graph. So with all these elements together, we have a huge structure, which is in the end the graph. So again, anything could be node and anything could be relationship between them. And to make even more advanced or even more full of knowledge, we usually put some links or some context or some ontology or rules over those nodes and between them. And in that way, we are not only presenting the content of various, but also everything that is known about the topic. So when we present an entity as a node, and we connect it with all links connected with the entity, we do not only represent interaction between two elements, but also everything about each of these elements, as well as about their. So we can build knowledge graphs of whatever. One more definition would be that it's concise and intuitive abstraction for a variety of domains, with relations captured between the entities. And then we can present social data, biological interactions. We can even make a knowledge graph of our platform. We can do knowledge graph of whatever we want that we could present in form subject interaction objects. So we always have a node which is interacting or influencing or affecting the objects. And then with accumulating such interactions, we are actually building knowledge graph. Usually at the end, we have some huge graph that could be then analyzed further. So 3 properties that could distinguish graphs from other graphs could be that they define real-world entities of the domain, so they show a part of the world. in form of graph. They provide relationships between them. So we do not have only elements that make some world phenomenon, but also relationships between them. And with that, we are able to infer new knowledge. And then we have all the data on a single place and better understand what it's all about. Now, it might seem like this is something really abstract and just somewhere done by some people, but actually we are usually in touch with knowledge graphs in our everyday life. And to tell you a secret, they are everywhere. So everything started with Aristotle, who liked to represent his knowledge and his concept in visual form. So actually, here we see his model of communications, and actually we see something that I shown in a way just a second before. We have nodes, and here we have labeled one interaction, and again node and node. So something really similar to what knowledge graph is today. Everything remained quite silent until 1972, when we think that we have used the term knowledge graph in the literature for the first time. But everything was raised on whole another level some 9 years ago when Google introduced its knowledge graph. And then other companies taken over the concepts like Airbnb, Amazon, eBay, Facebook, IBM, LinkedIn, Microsoft, Uber, and many more. And that the knowledge graphs just became a really hot topic. So the reasons for regaining the interest in knowledge graphs are not only that Google knowledge graph, but also that we had need to make better search engines, also to integrate the data more efficiently in a better way, in some other way, and also with rise of artificial intelligence because knowledge graphs and artificial intelligence are quite connected. So everything started from Aristotle. 1972 was the year that they were probably introduced in literature. They gained some speed in the meanwhile, and now the most prominent industries are using enterprise knowledge graphs. And here we can see some companies that are using knowledge graphs really heavily. And applications in these industries include something like search, web search, recommendations, systems, personal agents, advertising, business analytics, risk assessment, automation, and more. When I first introduced this platform, my guy from the team said something like, "Oh no, now we are going straight to research. We are talking about knowledge graphs, so we are pure science channel now." But actually, this is one thing then that actually was born in industry and then taken over to academia. It was too good for academia to ignore, and now it's everywhere. But everything started with industry. So why would anybody present anything? So first thing is that then that one could apply graph analytics to that knowledge graph and then gain some new conclusions and new data out of it. So graph analytics is application of analytical process to graph data. With that, we actually derive conclusions about nodes and their interactions based on the structure of the data. And many of its techniques came out from graph theory and network analysis, actually. If we go deeper to graph analytics, we will encounter a scheme, identity and context. So schema would be the higher level structure of knowledge graphs. Identity would be the very place of the node in real world. So which node in the graph refers to the same world entity, and context would be the specific setting in which some unit of knowledge is held in the true. Some examples of graph analytics would be, let's say, a centrality detection. It's all about understanding which nodes are the most important for the graph. They are used to better understand the roles played by different nodes. We have many centrality measures, and they are all calculated in different ways. We can see them here. And because they are all calculated differently, they all have different meaning when we try to interpret it. So with different centrality measures, we're actually getting different kind of conclusions. And we should know centrality measures when we should use which centrality measure. Also, example of graph analytics would be community detection, which would be identification of a group of nodes in a graph that satisfies some criteria of being in a community. Usually, the basic principle is that nodes in a community have more relationships within community than outside the community. And sometimes that could be the first step in analysis, and then we can process the analysis and the graph further. And here are some algorithms for the community detection algorithms. Then another example of graph analytics would be path finding. It's defining the path between two or more nodes that satisfy certain properties. Estimation of how well connected the graph is, estimation of how reachable or unreachable an element is, and this is very used in applications like the best route finding or route options or things like that.
Mila?
Yes?
I just wanted to maybe set a small pause here because it's like a lot of things going into the new topic, and also give you a small break. It's a very, very nice introduction. I'm trying to wrap my head around it. And I have a couple of basic questions, like, for example, just a practical one. So is there any limitation or minimal amount of size for the graph to represent something meaningful? So if I myself want to have some database of some small knowledge, would it make sense to create it out of hundreds of objects, or it's not really usable?
It depends on the problem. Like everything in statistics, you should know how hard and what kind of problem are solving, and then to adjust the number of nodes and relations. So there is no single answer to that question.
Yeah.
So it's very problem specific. Also, you could try with maybe graph with 10 elements, but then your inference will probably be not so good, let's say that way.
Mm-hmm.
When you have a huge graph, then you are gaining some accuracy and some precision and reliability.
Mm-hmm. And also a question about the relations or connections. So let's say if I have a knowledge graph about writers and their books, what is the best way to connect the book to the author? Should it be like bidirectional, or should it go from the author to the book, or the other way around? Oh, yeah. And what kind of links should I introduce? Like the author link?
You should always use only links in going from one direction to another, so not bi-directional links. And again, it depends on the problem. So you can represent some knowledge by any means. So you can represent authors and books as separate nodes. You can even add some more elements. And actually, there are some rules in building such knowledge base. Now it's getting more advanced. So if you know that the class of a book will change by time, then maybe you shouldn't just give a property to that node like just an attribute. You should represent it as a node and then connect it with the, let's say, gen. And by that, you can have to change that element. And if you are just assigned the property, you cannot that easily change the property also in graph. So it's getting more advanced, but the sky is limit, and you can represent knowledge however you think is the best for solving your problem. So it's again problem specific.
Mm-hmm. Yeah, and by measuring how good it's solving, I could use some of the measures that you mentioned before, or it's just another thing.
No, it's the end. In the end, it's again some accuracy, precision. At the end,
Mm-hmm.
it will again be some kind of classification, or usually classification, some maybe regression. So at the end, you are measuring the results by typical data science indicator, or
Okay.
by domain knowledge or common sense knowledge.
I get it. Yeah, now I think I connected it to my usual tasks.
Okay.
Perfect. Yeah, thanks.
You're welcome. We'll reach some of it later again.
Mm-hmm.
So, so we are somewhere in the middle of, let's say, basic graph analytics. What can we do with it? So also with graph analytics, we can find something like node similarity, which would mean that we are finding nodes that are similar to other nodes by some property. And here are some algorithms how we can do it. And of course, we have graph neural networks. These are special neural networks that are designed to operate on graph structures. Typically, we are doing tasks like supervised tasks, supervised learning. And let's say the specific tasks would be the classification of nodes, some predictions, and so on. And with this approach, now we have many applications, something like predicting the traffic, building recommendation system, verifying software, and so on. And because these graph neural networks are so powerful, they can even replace that simple graph algorithms that we talked about. And how we do it, frameworks and packages for it. So if you are using Python, you can try with NetworkX or scikit-network. And if you are doing it on a large scale and you need to cluster what you do, then you can try with Apache Spark GraphX, for example. Apart from that, network analysis itself, so previously about techniques that are actually analyzing the networks, call that structure as a structure. We also have ontology-based inference. These algorithms operate not only on structure of the graphs, but also take semantic into account. So all that context, all that meaning behind edges and nodes. And we have two categories of it, taxonomic inference and rule-based inference. With taxonomic inference, that primarily relies on hierarchy of classes and instances, and rule-based inference is more about general logical rules. And now let's go back to examples of knowledge graphs. So it was a bit abstract what it is and what we do with it. So again, everything that could be presented as subject, interaction, object could be part of knowledge graph. If we accumulate it, we will build one. And we usually do that for some advanced analytics or to gain some new knowledge out of it. So the most prominent example and how everything started is the Google Knowledge Graph, and believe it, you are seeing it all the time. So when you do a Google search, something like this will pop up on the right. They call it info boxes, knowledge panels, and this is exactly the extract from the knowledge graph. So behind this thing, info box, stands a huge knowledge graph of a Google, which is extracting or sourcing data from many sources. They only mention these Freebase, Wikipedia, and CIA World Factbook, but actually they want to keep some sources secret. So this huge knowledge graph behind it, and when you search something, you will get the extract out of knowledge graph. Same goes for Wikipedia. Actually, it has two huge knowledge graph behind it. So knowledge graph DBpedia and Wiki Data. So as you know, Wikipedia articles consist mostly of text, but also has that structured information, or again, info boxes on the right again. And there we can see some categorized information, images, other links to some other pages, and so on. So that's again the extract from the Wikipedia knowledge graphs. And they are operating on two of them. DBpedia is mostly used for these info boxes, while Wiki Data focuses on the data entered through its interfaces. So with DBpedia, it was structured. DB is coming from database. It is structured to provide that pop-up window, but we are allowed to semantically query relationships and properties of Wikipedia resources by that. So that knowledge graphs is further enriched with some external links and data sources like say, Drug Bank, New York Times, WorldNet, and so on. And with that, we can do some other things like some extractions, doing some parsing, or extracting something which is meaningful to us. Another example is Wiki Data, and it's actually the largest open knowledge graph available today. It's the central storage for structured data for Wikipedia. It's free, open, could be edited by anybody, can be read and edited by both humans and machines. It's huge. But actually, some knowledge graphs coming from industry are even more big, so even bigger. For example, they say that Google knowledge graph has something over 500 million entities with 18 billion of relationships. Another not so known name is GeoNames. It's dataset or database of geographical entities and features. So although these knowledge graphs at the start emerged as abstraction of organizing the all knowledge over the internet, they proved to be good for some other things like interaction with machine learning as a way to incorporate that world knowledge into machines. So that's the way how we can explain real world to machines. And we can combine machine learning and knowledge graphs in both ways. So we can use knowledge graphs both as an input and as an output for machine learning. So let's give some examples. So with connecting knowledge graphs and machine learning in a way that machine learning is creating something that will be a knowledge graphs, we have example like processing huge number of texts and then extracting the interactions out of it. So, and with combining all those interactions, we will build a huge graph, and then we can analyze it or make inferences. So, for example, serious financial companies are processing daily news, for example, combining all those daily news read by natural language processing with their internal database, so their information about their suppliers, about, let's say, delivery chain or something. And then as an output of combining those two would be the risk estimation. So if news are talking about bankruptcy of a company, and that company is our supply chain, we should know about it. So we should combine those two knowledges and to make some reasonable, let's say, decisions from it. So that's something that is done by some companies on a daily basis. Everything is quite automatic. News are, or tweets or social medias are processed by natural language, and that affect their business decisions. Also, if we put computer vision in front of machine learning, we now have object detectors, so it's part of computer visions that could actually extract that interactions from the image. So on one image, we maybe have dog sitting on the grass, or we can see how, let's say, a woman is carrying a bag. And with that kind of interactions, so subject interaction objects, we have pieces of knowledge graphs. Then we can then put in a huge graph and then analyze it in a typical knowledge graph analysis. With combining all those, so it's not just that we are just having one type of data that we can feed into knowledge graph. We can do everything. So we can theoretically, although that would technically be very advanced, to process all the news, to process all new images on social media, to feed it in a knowledge graph, and to use it in the way that we think it's the most appropriate for our aim. So with these machine learning techniques and algorithms, we can feed knowledge graphs and actually make graph models. On the other side, knowledge graph could be also an input to machine learning, and that's where the magic begins. So if we just build knowledge graph to best in a way that we think that our part of the world is represented the best, we can then turn it to convert it to numerical input, which is known as an embedding. So we are turning, let's say, words to vectors, graphs to matrices, and then pass it to machine learning algorithm and make something out of it. So with that, we are actually taking the part of machine learning, a very advanced analytic ability of machine learning to process knowledge graphs. So knowledge graph can be on both sides of machine learning, and wherever you put it in combination with machine learning, you are gaining something really powerful. One common debate is what is the knowledge base and what is the knowledge graph. So now we are going close to databases. So definition would be the knowledge base is a technology used to store complex structured and unstructured information by computer system. So the thing is that it's not always structured, but we should make a distinction. So the difference between knowledge base and knowledge graph is that knowledge graph has that graph structure, has that graph organization. And that might not always be the case with knowledge bases. So it could be unstructured. It could have all the properties of a knowledge graph, but it's not in the graph organization. So we can say that every knowledge graph is base, but not every knowledge base is a knowledge graph. If you have something to present, which is part of the world, you should also think of and representing that as a part of a database. You can also consider presenting that as a graph model and not as a relational model. So in relational model, we have all those tables, fine, but sometimes they are not so intuitive for, let's say, the user of that database, at least if you are using that just as a general view. But also we have more flexibility with graph models because we can easily add element anytime. We can start at any point. So with relational model, we should think in advance, so how it will look like at the end. But with graph model, we don't need to think about anything in advance. We could, and that would be beneficial, but we don't have to. We can just start adding the elements and then recreating something if it's needed. But you have much more flexibility with graph model than with relational model. And for people coming from tech world, some queries are actually more efficient when done in graph models. And also, as I said, the graph model will provide better understanding of the knowledge for the user. Luckily, we can make translations from graph model to relational model automatically. As I said, we can just start without thinking too much in advance. And graph model provides some more provide some more actions than usual NoSQL models. There are some limitations. So triples are not always representation. Sometimes we just have many elements that are just interacting at the same time, like reactions, for example, and then graph model is not the best way to present it. Also, time series data is naturally modeled in relations, and they are not the most appropriate choice when application contains only and primarily numeric data. Two popular knowledge graph data models are RD. Then we need to use query language Sparkle, and another would be property graphs, and then we query language Cipher. Property graph is an interesting subclass of knowledge graphs. And the main difference between other knowledge graphs and property graphs is that besides the nodes and relationships that we are showing, we can also incorporate properties of each node and each relationship. And they could be any sort of data. They could be categorical data and whatever. And that gives us even more opportunities to analyze it even deeper. So when we want to build the knowledge graphs, some basic process would be first to imagine what knowledge we want to cover and think about what information sources would be appropriate. Then maybe to align all that information, see what key pieces are, and then to actually do the mining, actually to pull the information out of sources and to put it in the graph. Graph in the end should be both machine readable and machine interpretable, and to enable some inference. Otherwise, it's just nice for watching, but it's not that much useful. We have some guidelines for each scenario, which I started previously in a short, in few words. So if you want to represent something, you have some guidelines, like we'll go through some of general guidelines later, but for example, everything that could be changed sometimes in the future should be represented as a node and not as a property, because it's easily to be changed. For example, if we just want to remove whole class of instances in our graph, it could be quite hard in one finished knowledge graph, which is complete and everything is so interlinked that wherever you want to remove whole class might disturb the whole balance of the knowledge graph. Usually, the inputs to knowledge graphs are quite different. So we have semi-structured, structured data, text, images, or human input. Usually it comes from many sources, not just from one database. We can do that extraction and branch generation both manually and automatically. Actually, I built my first knowledge graph manually and then turn to automatic generation of knowledge graph. Everything has its own pros and cons. Usually you should use some pre-existing database and not just pick the piece of information per piece of information from different sources. So pre-existing databases are really giving some quantum altogether that you can easily incorporate in a knowledge graph. They frequently different in structure, and how we are going to do it highly depends on what we are doing. So as it's stated here, the scale of the problem and desired accuracy. If we do it manually, we will gain more accuracy and we will know exactly how it's built and how reliable it is. But if we just want to collect a bunch of information, then we can do it automatically. And also for huge knowledge graphs like maybe that Google wants, it would not be so practical to do all that manually. So there must be some automatic part out of it. Sometimes the best choice is to just do it automatically and then to curate each relation by a human. But everything depends on what you are trying to do. If you are solving really important business problem and you really need accurate results, then it's the best to do it just manually. Specifically, we are building knowledge graphs with tools and platforms like these are. So IBM is even providing ready-to-use tool to extract information from Word documents and then to incorporate it in knowledge graphs. AWS Amazon Neptune is the tool for building knowledge graphs. It also enables some analysis. Neo4j is the most famous graph database platform. Then we have Azure Cosmos DB via Gremlin APR, Stardog, which is something like half product, so not that much programming you need for Stardog, and it is built for enterprise knowledge graphs. So once we build the knowledge graph, we want to make some use of it, and it's, as I said a few times, usually some new conclusions, something that is not explicitly shown on the knowledge graph itself, as something that we could not see in such a noise or such a bunch of information easily. If we have built a knowledge graph and we did analysis as we wanted, it's a pity to just leave our knowledge graph online. But in the same time, if you want to maintain knowledge graphs, it's not so easy all the time because they must evolve over a period of time. And then we have different change management techniques. We could change structure, view, truth. So in my case, I was building the molecular interactions graph, and then it's not so heavy because all that might happen is discover new molecular interactions, and then all I need to do is actually to incorporate that new molecular interactions into graph. Something like tracking the news or tracking the, let's say the news, because they might even different in the source. then you even sometimes have to remove the elements to do such kind of things. So let's say we are interested in truth maintenance, and we are following the news sources. So the maintenance of such knowledge graph is not so easy. So you have a bunch of conflicting news, and you should retain the vision of truth of the real world. So it's not always easy. And with all these graphs inside data structures, we have a new discipline which will be called graph data science. And as we said in the introduction, you can actually, which is not the basic thing, this great graph data science, but actually if you use some of these, you can advance or enhance or make better your results in other data science tasks. So for example, so the simple answer of how to have better performance of your data science analysis is to add some semantics in it. So to add the meaning of the data in your analysis. So for example, we can represent all that knowledge that you are analyzing by your data science task as a network, and then we can again connect it in both ways. So if we represent knowledge as a graph, we can take all the coefficients and analysis from that knowledge graph, then incorporate it back together with other data that you are analyzing. And with that, only with that, you should get better results than you would do just by let's say, pure data science. So however you are combining graphs and data science, you will probably gain some better performance. Now, when we are close to data science, we are also close to artificial intelligence. So we as humans, we deduce things quite easily. So it's something that we learn throughout the life. And when we see a knowledge graph, we can easily deduce what is happening over there. Even when we are not coming from the field which is shown on the graph, we can deduce something about it. And that general conclusion way of thinking, when shared by many people, could be named as common sense knowledge. But when it's shared just in a particular domain, we can refer to it like a domain knowledge. Anyway, machines don't have such abilities. We need to give them really strict instructions how to do something. And if we do so, if we explain to machines how to do that deduction specifically for a specific problem, for a specific field, then we can gain precision, efficacy, and scale even beyond human performance. So knowledge, that connection, they're capturing and codifying human expertise as a knowledge graphs, and then help machines to do whatever they do. So I found for a course, understanding is to a brain what knowledge graphs is to AI. But with this, we got something like, so with combining understanding the world and machine learning, we got something like personal assistants to get more things done, recommendation systems wherever to offer better recommendations, better search engines, and again, machine learning could even enhance building knowledge graphs by that extraction of entities and relations, but also in linking all that in one particular graph. Also could help us in anomaly detection, inference, question answering. And also the knowledge graphs are the way to interpret AI, because AI in general have a problem of black box problem, that something is going on, but we are not completely and precisely sure what is going on inside. So knowledge graphing is to overcome that black box problem. What should we care when we build a knowledge graph? We should care about end user. That would be the most thing to care who we care about. So general rules that we should present more information than a single user might be able to remember at a single time. We should cover everything, so user would not have to look for important pieces of information somewhere else, so it should be all there. By placing the relevant data next to each other, it makes it easier to make comparisons. And with letting the user interact with this graph, his engaging and understanding of the information presented will be enhanced. So we also care about other things, like, I'm just checking my internet connection. We should also care that data denting are accurate in that particular domain, or that grammatic rules or rules defined by the data model are accurate. Then we should care about that we should present the world like as it is. So we should represent the truth, real world. We should keep our graph up to date. It should be free from contradictions. We should avoid information overload and inclusion of data elements that are irrelevant for that particular problem or the domain. And it should be understandable by end user without some special guidelines. So at least we should provide human readable labels and descriptions. One more confusion that is often somewhere in air is what is the difference between knowledge graphs and ontologies, because if we look at them, they look quite similar. So ontologies are something more generalized. They're just systemized the knowledge, general knowledge, and that's it. But with the knowledge graph, we are going more to a specific use cases. When we add specific data of some specific individual data points and combine it with ontology, then we get a knowledge graph. So in other words, if we add data to ontology, we will then get a knowledge graph. And finally, some ideas and applications. So how companies are using all these knowledge graphs around the world. So some applications in finance are, I'll give the example of knowledge graph in Bloomberg. They use it for data analytics, including sentiment analysis for companies based on current news reports and tweets. That's what I said. They are reading news and tweets with natural language processors all the time, combine it with probably with their internal knowledge graphs, and have some specific analysis already done, which is giving them results in the real time. So something that could be close to sentiment analysis. They also use it like a question answering service and some, let's say, anomaly detection or emerging events that could happen in their field. Also, Thomson Reuters built a financial ecosystem for their needs, the knowledge graph of people, organizations, joint venture alliances, whatever, and use that for supply chain monitoring, risk assessment, investment research. Banca d'Italia, for example, use it to estimate the percentage of ownership of a company by various stakeholders, and other companies like Accenture, Capital One are using knowledge graphs as well. They are also used in other industries like healthcare is. So IBM is using for exploring new drugs, and also from extraction of the information from package inserts. And AstraZeneca is using knowledge graph to advance genomic research and understanding of the disease. In transport, Bosch are exploring knowledge graph of scene and location for driving automation. In oil and gas industry, Vismana use knowledge graph to mitigate the risk regarding oil wells and drilling. In insurance, they could be used as a fraud, waste, abuse detectors on insurance claims. In entertainment, they are used as recommendation engines for content platforms. They are also used in commerce. Amazon describes their products as parts of knowledge graph, and then the main goal is to offer user similar products at the end. eBay also encodes the product description, and shopping behavior also use that to enhance recommendations. Also, they use it to power conversational agents that aid users to find relevant projects to natural language inference. Airbnb encodes everything. It encodes places, events, experiences, neighbors, users, tags, everything. And then use that again for recommendations to clients, again of everything that was previously input to knowledge graph. Uber focused on their Uber Eats part of service, and with using graph, they are offering some places, food and restaurants for people that are not so sure what they would like to eat. So they use it for such recommendations. Of course, social networks take some advantage of usage knowledge graphs. So Facebook knowledge graph is not only describing social data about the user, but also their interests like celebrities, places, movies, music, and do all that to better connect people, understand their interests, and provide recommendations. LinkedIn also encodes everything: users, jobs, skills, companies, places, schools, everything else. And then use it for targeted advertising, to provide advanced feature for job search and people search, and recommendation for matching jobs to people and people to jobs. Pinterest is also using the knowledge graphs, I think only one, describing users and their interest, and it's all organized into a taxonomy. So that's like what specific companies are doing with specific knowledge graphs. But in general, in finance, you can apply knowledge graphs for financial analytics, calculation, reporting, know your customer better concept, anti-money laundering initiatives, financial crime prevention and investigation, and flow of money across the accounts. And in other industries, they are used for improving search capabilities, user recommendations, personal agents, targeted advertising, business analytics, connecting people, multilingual support, research and discovery, assessing and mitigating the risk, tracking news, and increasing transport automation. So again, the sky is limit. And sure, we all know about Alexa and Siri voice assistants. So they are heavily using this technology, because if you ask them a question, you don't want to have an answer that is connected with just spelling words. So if you want to know more about Eiffel Tower, if there is none, more appropriate answers will be something about Paris or something about towers in general. Then that I part. So the same word beginnings in case for Einstein, or maybe word ein in German, which means one. So you don't want, if you are interested in Eiffel Tower, you don't want to hear about Einstein, no, not even about German word, but you want to know about Paris and towers. So by that, this technology based on the meaning of the data and not just their similarity, really find their way to this personal assistance. So with this, I think I'm just checking. I think that we are close to the end. I just want to mention that in these slides, all this text is heavily influenced or should refer to papers. Here is one really huge paper in arXiv, really covering the topic on 150 pages. And there is a Stanford course CS 520 that you can see for more information. So that would be it for now.
Great, thank you, Mila. Yes, there are a couple of questions in the chat, at least so from Kartik, and I would read them out. I'm not sure if I understand them completely. So the first one would be, does any of the graph products support a rule-based inference to be coded into the graph schema as such? So I suppose you were mentioning a couple of products that support working with graphs.
Yes.
Is there anything connected with rule-based inference?
In that, if we are talking about that, we are talking about something mentioned that we like. Let me just check the exact term. That would be any second now. That general logic inference, just a rule-based inference. The products based on that would probably be something like things that are incorporating something like AND or whatever kind of logical rules. I don't have any product that I could mention in that context, but probably if one does not exist yet, it's worth considering building one.
Yeah, might be. Also, yeah, there was another question. I think you partly answered it in the later stages of the presentation, but anyways, so how do you apply ontology over the graph? Is ontology also represented as a graph? So you were mentioning schema is not.
Yes, ontology could be represented as a graph. And how do I apply it on it? Well, you can add all the elements to graph and then use formal ontologies, dictionaries, vocabularies, and any kind of systematized knowledge about the topic. And then, for example, when I'm using it for genes and for medical terms, I have vocabularies and databases of uniform chain names. And I just use links for that unique identification of that particular gene. And if you are talking about medical terms, then we have something like meshes, which is unique identification of each medical term. And then you can just add link to that specific identifier, which is available on the web. So with that, you are actually applying that already systematized knowledge to your own graph, or to add ontology to your own graph. So I don't know what other examples could be, but everything that is systematized somewhere even better if it's systemized in order to make it uniform on the whole world, could be then applied at least by links to knowledge graphs.
Yeah, thanks a lot for this answer.
And actually, all that ontology and systematizations and taxonomy could be presented as a graph, sure, but it's not going to be a knowledge graph until you add specific data into it.
Great. Yeah, I also will have a couple of questions from my side. They are less technical.
Okay.
So you were talking about how how knowledge graphs could be employed as an input and an output for different data science tasks. So if I'm using it as an input for some tasks, is there any easy and quick way to check the performance of my graph? So if I want to use the embeddings afterwards in some model, can I somehow be sure that my graph is okay, or it's only trial and error?
Are we talking about how good your graph is, or how much performance gain you will have?
So let's say my main task is to solve the data science task, like to create a nice recommender system, I don't know. And for that, I would like to use embeddings from the graph.
Okay.
And should I go like to the biggest graph I could collect, or I could somehow check how my graph performs in the meantime without doing the whole pipeline? Like maybe there are some, so there are a lot of these measures, maybe I could use some of them.
To the best of my knowledge, until you build that graph and actually analyze it, you cannot be sure. So until you go all the way through that process, you cannot be sure what kind of benefit you will have. The better you represent your data by a graph, the more efficacy you will get out of it. So if you add at least some semantics, so at least some meaning to your data, it should make your performance better. But actually, I found some papers with gaining only 2% of let's say better accuracy, but it was a quite complex setting where images were analyzed, more sample size, and so on. So it should improve at least a bit your analysis, but you don't know at the end how much it's going to use.
Yeah, I mean, we live in the world of uncertainty.
Yes.
I was hoping for a silver bullet.
Actually, if you can find that some of the automatic readers or collectors for your domain task, you can fastly maybe try with collecting that knowledge and incorporate it into knowledge graph automatically, and then maybe see how your analysis is doing with it. But anyway, if you are really serious about an analysis, then you should maybe curate that data graph or that information which is incorporated in it before you do something serious.
Good.
So, for example, reading millions of pages takes not more than a few hours, and if you do it manually, you will lose, I don't know, forever to do it. And then you're yes, and then if you are talking about try and error, it's faster if you try it automatically.
Yeah, thanks. And so another question regarding closer to this about these embeddings. So other typical ways how to get embeddings from the graph. So these packages that you mentioned, they could handle it, or I should?
Yes, they could handle it in both network X and scikit network. You have algorithms which are ready to use, and I think you also have different kind of embeddings and use or try them and then to just use it. Perfect. So it's part of the network analysis, yes, and these packages would not be good network analysis packages if they wouldn't provide it.
Yeah, who knows? Right. And yeah, maybe yeah, I should wrap it up. Is there any database that holds some interesting and fancy graphs that one could explore? I don't know, the graph of musical bands, the graph of books.
Usually with Wiki Data. So actually, the Wikipedia is not so reliable source of information because everyone had edited. So we were witnessing some situation then when all articles were changed in order to make it like more fun, but that kind of thing would disturb your analysis or whatever you're trying to do. But go to Wikidata and see what is happening over there, so you can parse, retrieve, and analyze whatever. So it's good because you have many things already extracted, and then you can just query it, combine it, and analyze it. You then skip that extraction part. You then skip that part of choosing what database should I use and how reliable it's gonna look represented as a graph. So they are in a way taking care of that representation that holds true, and then you can just query and analyze it, and it's like half work done.
Cool. Yeah, I should start from that.
You can try.
Yeah.
Thanks, Mila. For me, it was some new material, not a question, but a comment. Indeed, connecting some of the dots, I realized that I have a little bit knowledge about that, but indeed, that's a different area. I can spend a whole eternity to explore. So thanks for increasing the amount of data I should dive into.
You're welcome. You're welcome.
Yeah.
You're probably a better person to cover all these topics in the beginning. So OWL and RTL.
Yeah, a lot of abbreviations.
Yes.
They haven't heard it.
You are now responsible for all the issues. So.
Yeah.
Good. Yeah, so I think we could maybe try to wrap it up. And before, we probably could answer the question, who will invent the general AI? Will it be Wikipedia or Google with their knowledge graph?
No, it's still, they are trying, but it's still far away from what they imagined that it would be. But they say the one that has more data already has its own competitive advantage. But with all that connecting AI, inputting data into knowledge graphs and then being analyzed machine learning chain, something is still missing and something is still breaking that vision and idea, and still there is a lot of things to be done before it's possible, even in some, let's say, meaningful. So it's
that's perfect.
full of yes, that's perfect.
I have my job.
I agree. Yeah. I agree.
Yeah,
it's nice when you have just an elements, but you should not be taken over artificial intelligence in general.
Good. Yeah, I suppose with this positive note that we're not going to be fired soon or anywhere soon, we could call it a day. And wish everyone a nice weekend. And thank everyone for joining us. So we are here for you and happy to discuss and share knowledge with you. And for sure we will have next events. I most definitely in September. We're not gonna announce it today, but stay tuned to all our channels, Telegram, Eventbrite, and all of them. I see that there is like one very late question in the chat. I suppose we could cover it quickly.
Yes.
So if I understood well, can both nodes and links have features?
If we are talking about these property graphs, then you can add whatever you want to both entities and nodes. any kind of attributes, whatever you want to, numerical attributes and properties, categorical, you can add it.
Yeah. Awesome.
So let's say
Well,
if we are connecting Igor with his, let's say, age, place, interests, and so on, and then we have friend interaction going to Alex, at least for that friend interaction, we can add something like how long they know each other, see, which is like a life study could incorporate data like how long do they know in these years or whatever. We can add the place where they met. We can add their, let's say, areas of interest that connected them and so on. So we can add whatever to that interaction.
yeah, you're reviving too many nostalgic memories.
I know. I'm proud of you guys.
Good. Yeah, I think we had a pretty nice session, and you covered all the most things about knowledge graphs. I'm really keen now into going deeper in this topic. Thanks for mentioning some sources.
You're welcome.
Yeah. Well, I would say let's again say see you later and have a nice weekend.
Bye, everyone. Have a
Bye-bye.
nice
See you.
weekend.
Enjoy.